Hi, I'm going to go over quiz 1. There are two different versions of this quiz, but they're both pretty similar. Both versions show two situations. One where I have a 20 kilogram mass on a ramp, goes down a ramp and compresses a spring. This one starts with the spring compressed with a 1 kilogram mass, and then the spring pushes the mass up a ramp. We have two things that we're solving for here. One, the maximum velocity of the 1 kilogram mass. Two, the maximum height, I'm going to label as h, of the 1 kilogram mass as it goes up the ramp. This is a problem in energy conservation. Whenever we do a problem in energy conservation, we need to figure out what the equation is for each of the individual components of energy. I'm going to write down the equation telling us what the total energy of the system is. The total energy is equal to potential energy gravitational plus potential energy of the mass spring plus kinetic energy. These are all the different types of energies we need to be concerned with in this system. Potential energy gravitational is mass times gravity times height. Potential energy of the mass spring is 1/2 kx squared. Kinetic energy is 1/2 mv squared. When I look at these different energies, I try to figure out, is there any of this type of energy in this system? Well, I look at the indicators. What I mean by indicators is what indicates that there's gravitational potential energy. The indicator is that there's some height associated with the system. Clearly, gravity always exists. We have a mass there, but the mass, if it's down here, doesn't have potential energy gravitational. While if it's up here, there is gravitational potential energy. And the height is the vertical distance above its equilibrium or its rest height, wherever it'll come to a stop. In other words, we're assuming potential energy gravitational when it's down here is 0, so that we have some difference up there. Potential energy of the mass spring system, the indicator is x, which is the compression of my spring. Kinetic energy, the indicator is velocity, which is the velocity of my mass. We want to find out the total energy of the system, and let's look at the top situation here to determine that. The total energy for I right here, we'll call this AI, equals, is there gravitational potential energy with this system? And yes, there is, because there's some height associated with the mass. So the gravitational potential energy is 20, the mass, times 10, which is gravity, times our height, which is 3 meters. Is there potential energy mass spring associated with the system? Well, the indicator is compression of the spring, and the spring is not compressed in this situation, so there's no mass spring potential energy. Is there kinetic energy associated with this system? Well, this is the starting position of the block. It has 0 velocity. If I let it go, it'll start gaining velocity, but when it's at its maximum height, its velocity is 0. And since velocity is an indicator of kinetic energy, there's no kinetic energy in the system. So the total energy of my system is 600 joules. Now I have another situation down here where I compress this spring, and we compress it 2 meters. What is the total energy of the second situation? The total energy of the second situation is still 600 joules. Why? Because energy is conserved. The energy changed from potential energy up here, turned into kinetic energy as it sped up, and then all that kinetic energy turned into potential energy of the mass spring as it compressed it. When it's completely compressed, as it is in this situation, there is no more kinetic energy because it's at a stop. It's all inside of the potential energy of the mass spring system. We can use this to determine what the spring constant is. We actually don't need to figure out the spring constant for this situation, but let's go through that exercise anyways. In the second situation, the total energy is equal to, again, these 3 energies. Let's figure out which of these energies we need to be concerned about. In the second situation, there's no height, so we don't have to worry about potential energy gravitational. The mass spring system is compressed, so we are concerned about that. 1/2 kx squared. In the second situation, again, there's no velocity. It's at rest when it completely compresses the spring. That is, the velocity was in this direction, compress the spring, velocity goes to 0. If I let it go, it'll start going in that direction. But at this moment, when the spring is completely compressed, there's no kinetic energy. And so our entire equation looks like this. We can plug in our total energy, which is conserved, equals 1/2. We don't know what the spring constant is. We're solving for that. But I told you that the spring was compressed by 2 meters. So we can solve for this. 600 equals k times 2. K is equal to 300. And this will be in newtons per meter. So our spring constant is 300 newtons per meter. We can use this for this situation, but we don't quite need to. Let's do it anyways, though, just for the fun of it. So we have a second situation. This is where our questions all dealt with. We had the first situation just to let us know about the spring and what the spring constant is. Now we can apply it with the use of a new mass. The total energy of the system in this situation, let's call that B sub I, total, equals the potential energy. Is there any potential energy in the system? Gravitational. There's no gravitational potential energy because there's no height associated with our 1 kilogram block. So we don't need to worry about that. What about potential energy of the mass spring system? There is potential energy in this because I start with the spring compressed by 2 meters. So this is equal to 1/2 kx squared. Is there any kinetic energy associated with this situation? And no, because our block isn't moving, it's at rest when the spring is completely compressed. So the total energy of the system is 1/2 times k, we solved for the spring constant, 300, times x squared. Our compression is 2, so 2 squared. 1/2 times 300 times 2 squared will give us 600 joules. We find out the total energy of this situation is the same as the total energy of this situation. And that's because the spring is compressed by the same amount in these two, and the potential energy of the mass spring system doesn't care what the mass is, it only cares what the spring is. Now we can just use intuition. If I compress the spring by 2 meters and have a 20 kilogram block, it'll go some height up this ramp. If I compress the spring the same with just a 1 kilogram block, we expect this to go a lot further up the ramp. So one question, first of all, is what is the maximum velocity? And then the next one is what is the height? Let's determine the maximum velocity. First of all, we have to determine where will the maximum velocity be. If I let go of the system, the velocity will speed up. It's going to get at a maximum when the block is right here and the spring is completely decompressed. It's going to be a maximum because right after it starts to go up this ramp, it's going to slow down. And so the maximum will be when the spring lets it go. It's moving at its max velocity between this position, and then it'll slow down as it goes up the ramp. We can use energy conservation to determine that maximum velocity. Again, E total equals these three, superposition of these three energies. Is there any gravitational potential energy when it's right here? No, there's none because it's not actually started going up the ramp yet. Is there any potential energy associated with the mass spring system right here? And no, we're looking at a point where the mass spring is completely extended, so it's at equilibrium position, and the mass is disconnected from that. Since this is at its equilibrium position in the second scenario, there's no x, therefore there's no potential energy. In fact, it's all kinetic energy. That makes sense. The maximum velocity should be associated with the point where all of its total energy is in its kinetic energy, in its movement. So we're going to solve for this equation. 600 joules equals 1/2, mass is 1, and we're solving for the velocity. So the velocity squared is equal to 1200. Velocity is just going to be the square root of 1200. I'm not even going to simplify it further. We could leave it like that, and that'll be in meters per second. Okay, we determined the velocity because we said when the velocity is a maximum, all of its total energy will be in its kinetic energy. This is square root of 1200 meters per second. Now let's do the same type of application of conservation of energy to how high does this mass go? Well, again, we look at our equation for the total energy. When this mass, let's write our equation out, E total equals, when the mass is up this ramp, there is potential energy associated with it. And so this will be equal to mgh. When the mass is at the top of the ramp, is there any potential energy with the mass spring? And no, we know that mass spring already extended all the way, it's in its equilibrium position. So there's no x. X is how far is it from displaced from the equilibrium position. Is there any kinetic energy? When it reaches the maximum height, that is when the velocity reaches zero. That is, the velocity is pointing up here, but it gets slower and slower, velocity is zero, and then it starts to go down. So at the maximum height, velocity is zero, and our entire equation looks like the total energy is potential energy gravitational. We can plug in our numbers for this. Equals 1 times 10 times height is what we're solving for. And we learned that the maximum height of our mass, of our 1 kilogram mass, is 60 meters. And so those are the two answers to this problem, where the velocity is root 1200 meters per second and the maximum height is 60 meters.